we take M1, M2, M3 to be simply the initial monomials of the three generators, the standard basis of the net. And so this we do this when we're trying to prove semi-stability. What the instability means, and that is unstable if we can write it, we can choose a basis Q1, Q2, Q3 of the net such that there is a one parameter subgroup rho satisfying the following property. If we take the initial monomial with respect to rho of Q1, of Q2, and Q3 and add up their weights, the weights are negative. The sum of the weights is negative. So I'll illustrate the instability on an example later on. I don't want to write it down. And so what I want to do now is I want to first give an idea of how we can analyze the semi-stable points in this Grassmannian. And I'll do this by stating a theorem. Okay. And well, this is right. This is all the theorems are joined. All the results here are joined with David Smythe. And so let me indicate that this is all work here is joined with David Smythe. And this everything here already appeared in a paper, which will be which is available on my webpage, for example, but it's not on the archive yet. So the theorem is a net, and that is semi-stable if it is semi-stable. Sorry. It is rho I semi-stable for all one parameter subgroups rho I of the following numerical types. Okay. And right. Okay, this is slightly unorthodox board work, but so this is a board is a continuation of this statement. All right. Okay, and we can reformulate this as saying that the net is unstable if and only if it's destabilized by one of these one parameter subgroups in some torus. So what a numerical type of a one parameter subgroup is the 5 tuple of these weights with which it acts on a vector space diagonally. Okay. All right. So all of this one, we won't use all of them, but let me indicate how we prove this theorem. I mean, in theory, there should be an algorithmic way to do this, and we did this by hand. So the argument is slightly ad hoc. So the sketch of proof. Well, suppose we have a net which is rho I semi-stable for all I in this list, but which is destabilized by one parameter subgroup chi acting on the basis diagonally with weights weight of A through weight of E, And well, I can't. It's going to be a sketch, so this is. I'm just going to do a special case. I'm going to consider a very special case. I'm going to look. Well, going to make two restrictive assumptions. A is that the weight of A plus the weight of E is, say, greater or equal than weight of C. If you look at our conventions, this inequality describes exactly half of the one-parameter subgroups, which is, of course, doesn't. I mean, we need all, but let me just do this one. And B, I'm going to assume, and this is much more restrictive. I'm going to assume that the point defined. I mean, we have this. We have a filtration on the vector space. We have a flag of linear subspaces, and when we take the point and the flag, we're going to assume that this point is not a base point of the net. Okay, and I'm going to arrive at a contradiction now. Okay, so how do we do this? Well, what does B say? B says that. Assumption B says that the initial monomial of Q1 in the lexicographic order is A squared. Right? If it was not A squared, it would mean that the whole net lied in the ideal generated by B, C, D, and E. All right. Now we have to use now semi-stability with respect to rho i's. So let me observe that rho 3 semi-stability implies that the initial monomial of Q2 is at least B. All right. Well, why is it so? Well, otherwise the Q2, Q3 all lied in the square of the ideal generated by CDE. And well, this is impossible because in that case, the weight of Q2 and Q3 of all monomials in Q2 and Q3 would be -4, and the weight of the monomials in Q1 would be at most 6. I mean, it will be precisely 6. Right? So the reason here is that 6 plus -4 plus -4 is negative, and this contradicts rho 3 semi-stability. And finally, well, I need one more. Let me just go back. Let me go back here. Rho 4 semi-stability implies that initial monomial of Q3 is at least, say, greater or equal everywhere. Yeah, so this is greater or equal, is at least D. Otherwise, Q3 is a square of a linear form. In other words, our intersection will be degenerate and generically non-reduced. And this contradicts, if Q3 is E squared, then with respect to rho 4, the weight of Q3 will be -8, and the weights of Q1 and Q2 will be at most 2 each. So that would be unstable with respect to rho 4. And so now let's summarize. So summarizing, we have that the weight with respect to chi of the 3 initial monomials is at least 2 times the weight of A plus weight of B plus weight of D plus 2 weight of E. And since all the weights add up to 0, this is which we assume to be non-negative. Right? It was a very strong assumption, but we're done in this very special case. And then, well, to finish the proof, we have to consider the remaining couple of dozens of cases, and we do it one by one. Okay.
This, but then, I mean, you can remove to each cases, but how do you look at this this term?
How do you find them? Okay, so the way we did this was the following. We start with a list, and then we try to prove the theorem. And if you can't prove the theorem, it means that you're missing a one-parameter subgroup. And at the place where the proof fails, you find the extra one-parameter subgroup, so you add it to the list, and then you try to prove the theorem again using our procedure. And after 12 iterations, you have a theorem which you can now just prove without finding the one-parameter subgroups. But I mean, there is in principle I've just an algorithmic way to find this one-parameter subgroups based by, we look at the state Polydov of the Grossmanian, and you look at the maximal unstable states, I guess, or sets. Okay, and so now I want to state a yes.
Is there any approximation to the numbers of subgroups you need?
Approximations? Oh. Can you estimate how many subgroups you need a priori? I don't know. I don't know. I don't even know the answer in the case of, say, hypersurfaces in projective spaces, where it's easier. Okay. So let me state a corollary here. Corollary. A semi-stable net defines a complete intersection curve. I guess a complete intersection, which will be then a curve. All right, so a priori it's not clear that a semi-stable net will define a curve, because you could have a intersection of 3 quadrics which had a 2-dimensional, 3-dimensional component. Right, and so using the list of the one-parameter subgroups, we can quickly rule out those possibilities. Okay, so let me just sketch the proof of the corollary. Well, if I contains, and now we'll sort of abuse the language and say that a net contains a hyperplane. If the intersection of 3 quadrics contain the hyperplane. So if I contains a hyperplane E equals 0, what it means that all the quadrics are divisible by E, and then it's destabilized by row 4. I think it's row 1, right? And I think I had a... I'm sorry. So here I was slightly confused. I had to use row 1 in my proof, not row 4. Okay. So it's destabilized by row 1 because the weight of each quadric will be at most -3, which is negative. If I contains a plane, let's say given by the equation d equals 0, then it's destabilized by by row 2, because then the weight of each quadric in the net is at most -1, which is the sum of 3 weights is negative. If I contains a surface component, so we've ruled out all the components of dimension 3. The only possibility is a hyperplane. Now, if you have a surface component in the intersection, it can be either a plane or a quadric. Well, if you have a quadric in the intersection of 3 quadrics in P4, then a pencil in the net will contain a hyperplane spanned by the quadric. So this means that, let's say that the pencil Q2, Q3 contains equals 0, which means that they were destabilized again by row 1. And there is one more case that remains, namely when the surface component in the intersection has degree 3. And this surface, the only possibility for the surface is a Hirzebruch surface, which is cubic rational normal scroll, and it has already appeared in the lectures of Giorgio and also at Sushi yesterday. So if I contains a cubic surface, then by a result of Del Pezzo, the classification of minimal, goes back to Del Pezzo, the classification of minimal surfaces, we know that the surface is a cubic scroll, and it's given in some coordinates by the following equations. And in particular, the net must be precisely given by those 3 quadrics, and it's destabilized by the 1-parameter subgroup 4, 4, -1, -1, -6. All right, so let me check this. Looks right, and this is the row 6. In the list. So there are no higher dimensional components. All components are curves, and we're done with the corollary. All right, so I can now state another result, which is essentially a complete classification of semi-stable curves in this Grassmannian. So from now on, when I say semi-stable curve, I can replace the phrase semi-stable net by the phrase semi-stable curve, because all semi-stable nets are curves. So a curve let me first describe reduced semi-stable curves. A reduced semi-stable curve is an element, is a divisor in a linear system, complete linear system of this form. So it's a quadric section on a smooth quartic Del Pezzo, which I'll write as a blow-up of P2 at 5 points. And so this EI says the exceptional divisors of the blow-up. And it's smooth which is, and now, well, not all divisors in this linear system will be semi-stable, and I have to tell you which one are not, which is, that is not of the following forms. And then we have to describe unstable divisors in this linear system. Well, the first item in my list is non-reduced, and it's perhaps, yeah, I guess, strictly speaking, this is, yeah, this is necessary, right? Because I'm describing reduced semi-stable curves. And then I'll just draw pictures of the non-stable curves in these linear systems. We have a curve with two triple point singularities, and we have I'll indicate the degrees. The degree here is 2, 2, and 4. So a conic, and a rational normal quartic, actually an elliptic quartic, meeting in 3 points. This curve is unstable. So let me, just as an illustration, draw the pictures of all unstable loci of curves on smooth Delpetzos. We have a curve where we have two quartics meeting in a node and in an A5 singularity. A fourfold point, a planar fourfold point with two branches being lines is unstable. But any other fourfold point, ordinary fourfold point, will be actually semi-stable. So let's see. We have the following picture: two conics which are tangent and which meet the remaining quartic in two nodes and a D6 singularity, a D5 singularity. So D5 singularity is a tag node with a transverse branch. And there are two more. So for completeness, let me write them down. Have a curve like this. A D5 singularity is a cusp with a transverse branch, and here is a normalization of the curve is a hyperelliptic curve and such that P1 plus P2 is a G12. So this is not allowed. And finally, a genus 2 curve. Let's call this one, this component C naught or C tilde. This is the A7 singularity local equation y squared equals x to the 8. And then what is, if we call this point P, if P is a Weierstrass point on the genus 2 component, this picture is not allowed. Okay. And everything else is allowed. And so the way one proves this theorem is by simply going through the list of the one-parameter subgroup, and for each one-parameter subgroup describing the curves which are destabilized by them. And so there should be a correspondence between one-parameter subgroups and pictures that I drew. Of course, we have more one-parameter subgroups, and the reason is that some are used to destabilize the intersections with surface components, and some are used to destabilize non-reduced intersections. So let me now describe non-reduced intersections, and that's the second part of the theorem. A non-reduced or non-reduced semi-stable curves R, and we have a list of 4 different types. First, we have the so-called balanced ribbon. This is the ribbon that we saw yesterday, a particular case of genus 5, and the equations for this ribbon are as follows. Okay, I don't. So yesterday I've defined the ribbon parametrically, and if you work out the equations, you get these 3 quadrics. If you go from the parametric representations in the basis I gave yesterday to the equations, these are the 3 equations one gets. So this looks like a rational normal curve with a double structure. And there is only one such thing. So there is a single closed orbit of semi-stable curves which look like double structures on quartics. And there are 3 more cases. I don't want to go through each of them carefully. So let me just say a double twisted cubic meeting a conic in 2 points. A double conic meeting a rational normal curve in 3 points, and 4 2 double lines joined by 2 double conics, 2 double lines joined by conics. And there is precisely one closed orbit of semi-stable curves which have a double line. So this is a picture and there is an equation for it. Okay. So we have a good control of what curves appear in this in M. All right, and so let me say maybe just 2 words about the proof. So one key observation is that if the semi-stable curve is reduced, it lies on a smooth del Pezzo. And the way one proves this is having a net, we'll look at the discriminant of the net, which is a quintic in P2. And one has to show the general line in the general pencil in P2 will give us a quartic. And to have a smooth quartic del Pezzo, we need the discriminant to be non-reduced. And so what we do, we go through all the possibilities, the discriminant to be reduced. And so what we do to prove this part of the theorem, we go through all possibilities for non-reduced discriminants of nets. And we destabilize most of them. And when we can't destabilize, when the net is actually semi-stable, we observe that it comes from this list. So the curve, the resulting curve is non-reduced as well. And from this it follows that a reduced semi-stable curve lies on some smooth del Pezzo. Of course, the quartic del Pezzo is not unique, unfortunately. All right. Now the proof of the, let me just, to connect with the yesterday's lecture, let me just quickly observe why the balanced ribbon is semi-stable. So the part of the proof, the semi-stability of the ribbon, which we did yesterday in a slightly different language. But since we have the equations here, we just let me observe that if one takes the set of all 15 quadric monomials in variables a through e and throws away the three ones, AC, AE, and CE, then the weight of the resulting 12 monomials with respect to any one parameter subgroup acting diagonally on this basis is -2 of A plus C plus E. And if we throw away three other monomials, namely B square, BD, and D square, we get the weight which is -3 of B plus D. And these have the opposite weights. And what this shows that with respect to any one parameter subgroup acting on the basis A, B, C, D, E diagonally, the ribbon is semi-stable. And the Kemp theorem, which we applied yesterday, allows us to conclude. And the reason is that we have a GM action on the ribbon given by weights 2, 1, 0, -1, and -2. Right, so what I did, I just repeated the proof of the semi-stability of the ribbon from yesterday in the case of genus 5, slightly sketchily. Okay. So now what do we do with this classification theorem of semi-stable curves? We can use it to show that the GIT quotient M is the log canonical model of M5 bar. Okay, so let's see. So theorem. Well, there is a rational map by construction from M5 bar to our GIT quotient M. And we show that this is a birational contraction. Namely, it's birational and it is a contraction. That is, the inverse map does not have any exceptional divisors. And it contracts three geometric divisors on M5 bar. We have a divisor delta 1, and it contracts, the map contracts delta 1 to the A2 locus. So this is a locus of curves with cusps. Contracts delta 2 to the A5 locus. And this looks like A5 locus looks as follows. To define what an A5 curve is, take a genus 3 curve and embed it, genus 3 curve C, and embed C by a canonical system twisted by 3 times a point in P4. Then the point P becomes a flex, and when we take the union of the curve C with the flex line, we get a complete intersection of 3 quadrics. And the singularity here is y squared equals x to the 6, which is an A5 singularity. And so the way this map works is that if you have a genus 2 component attached to a genus 3 component would take the genus 3 component embedded by this linear system, canonical twisted by 3 times a point, and we introduce a flex line, and we get an A5 curve. And so it shows that the map is, well, the description suggests that the map is regular along that locus, as it should be because the delta 2 is a divisor. And finally, the trigonal divisor. Right, so M5 bar, or M5, has a divisor of trigonal curves, a Brill-Noether divisor. And it's, well, you can't find a trigonal curve in our description of semi-stable curves because a trigonal curve lies on a cubic scroll. So the second Hilbert point of a trigonal curve is the second Hilbert point of a cubic scroll, which we've destabilized. And what in fact replaces a trigonal curve is a trigonal divisor is a single curve which is defined by the equations AD minus BC B. And so so the picture of this curve is one has a triple conic, so triple conic union 2 lines. The reduced structure of this non-reduced curve lies on a cubic scroll, so it's trigonal. But the scheme theoretically, this curve with its triple structure along the conic does not lie on a cubic scroll, so it's a non-trigonal curve. All right, so let me finish the statement of the theorem. We can pull back precisely the O of 1, the line bundle, the ample line bundle on the quotient of the Grassmannian. And we can compute its pullback in terms of the standard generators of the Picard group. And from this, we can conclude that M is precisely M5 bar of alpha, where I use the notation from yesterday, where alpha is any number from 3/8 to 14/33. Right. Okay, so I'll finish by sketching the proof of parts of this theorem. So let me in words explain the first part. Why do we have a contraction? This follows from the description of the semi-stable locus, namely the locus of non-nodal curves in the semi-stable locus is of codimension at least 2. So the inverse map from the quotient to the M5 bar is not defined along codimension 2. And it does not contract any divisors because all nodal semistable on the locus of nodal semistable points, the inverse map is an isomorphism. Okay, so we have a contraction. Now, how do we know that delta 1, delta 2, and trigonal divisors are being contracted? Well, we'll look at the loci. So we'll look at the A2 locus. From the description of semistable points, or from the description of unstable points, we know that the A2 locus lies in the semistable locus. So if you take now A2 curve, the curve with a cusp, and you perform the stable reduction, you get precisely a curve in delta 1. And if you take an A5 curve and you perform a stable reduction, you get precisely a curve in delta 2. In fact, you can get a generic curve by taking a generic A5 curve and picking the deformation correctly, the smoothing correctly. And now finally, we have this triple conic union 2 lines. We know it's semi-stable. I'll indicate in a second a quick proof of that. And we need to do the stable reduction. The stable reduction is a little complicated. It involves syzygies of trigonal curves. But if you do stable reduction, you can show that you can get a generic trigonal curve by performing stable reduction. And that finishes the contraction part. Now, I'm going to now focus in the remaining 10 minutes on these two statements. And this involves a nice, not just a simple but pretty observation. Namely, let me start with let D in the Grassmannian be the I just write it in symbols. Let D be the set of nets in the Grassmannian such that I contains a rank 3 quadric. Then D, by dimension count, D is an irreducible SL5 invariant divisor on the Grassmannian. In particular, by the definition, by the Mumford's definition of semi-stability, everything which is not in D is automatically semi-stable. So the complement of D is semi-stable. And now the observation is, let me give a name to this triple conic I sub T. The net defining the triple conic does not have any rank 3 quadrics. I mean, this is a computation one has to make, right? And this implies, in particular, that IT is automatically semi-stable. So we have semi-stability, but it also gives us slightly more. It tells us that when we pull back the divisor D, just take its preimage to M5 bar, we're not going to see the trigonal divisor in the preimage. There are two more observations that we have to make, and they are A2 locus and A5 locus are not contained entirely in D as well. This one has to prove by exhibiting just one curve from each locus which does not lie in a rank 3 quadric. And so by abuse of notation, I'm going to write, we have D in M, which is a quotient. This is the image of the divisor D in the quotient. Is irreducible. Divisor, and its preimage in M5 bar, while D does not contain the centers of the exceptional divisors of the rational map F, so the preimage of D is going to be irreducible divisor. And now geometrically, if you have a canonical curve of curves, C such that if you have a canonical curve lying in a rank 3 quadric, geometric consideration tells us that the canonical divisor of such a curve is 2 times the line bundle, so you have a theta characteristic L, which is even and which is degenerate. I guess there exists such that there exists L for some L. Right. So this line bundle is just a pullback of O of 1 under the projection from the vertex of the rank 3 quadric. And if the vertex meets the curve, then you get a trigonal curve. But if it doesn't, which is a generic case, you get the even theta characteristic of with h not actually being 2. I mean, you can't have 3 as I understand. Well, okay, and so this is a so-called vanishing theta null divisor. And by a theorem of Taxidori-Bigas, its class is proportional to what we have before. And so as geometric considerations gives us the proof of this part. And to finish, let's just do a simple computation now. So let's summarize. We have a rational map, right? I mean, so D on the quotient is some multiple of O of 1, because there is just one line bundle on the Grassmannian, and on the quotient, its pullback is proportional to the vanishing theta null divisor. And we observe that if we take canonical divisor on M5 bar and add 14/33 of delta and multiply by this number, we get precisely this number, or this divisor class. And this is from above pullback of O of 1 plus some positive multiples of exceptional divisors. All right, in particular, M5 bar of 14/33, which is by definition is a proj of the graded ring of this graded ring by the projection formula. This is the same as a proj of the graded ring on M of O of M. And since O of 1 is ample, this is just M. So this shows that that M is a log canonical model associated to the alpha equals 14/33. And now where does 3/8 come from? Well, the fact that the trigonal divisor is contracted means that push forward of the trigonal divisor is 0. The trigonal divisor on M5 bar has class A lambda minus delta naught minus 4 delta 1 minus 6 delta 2. Delta 1, delta 2 are contracted, and so this implies that 8 lambda equals delta on M, and this implies that Km plus 3/8 of delta is just 13 lambda minus 2 delta minus 16 lambda plus 3 alpha is just 0. So the log canonical model at alpha equals 3/8 becomes empty, because it asserts that this log canonical divisor is trivial, and so we're done.